Hey guys, this is Landon Chambers going over your most asked questions during this week's recitation. So let's just start over here. The top concerns this week were where to start in problems, vectors in general, how to express them, how to do the quiz, which dealt with adding two vectors, and also the constants of integration we get whenever we're integrating, acceleration, and velocity. How to deal with those, okay? So I picked two problems to look at to go over these things, all right? And the two problems are, well, the problems we looked at in recitation. Exam 2012, problem 4, so this is exam 1. We can pull it up real quick. It's this problem, okay? And the other problem is going vector quiz we did in recitation. So with the exam 2012 problem, we will address where to start with problems like this and what to do with the constants of integration. Also, in the vector quiz, we will address some misconceptions about vectors and also just some more about vectors than what we talked about in recitation. Okay. So I have this all written out this time. All my work is all written out because otherwise this video is going to be very long. Okay, and I don't want to waste too much time here. So go ahead right now and pull up Exam 1 2012 Problem 4 and read through it. Okay, so there's one clarification on the problem, and that's the drone must hit the car when it reaches the tunnel. Okay. So let me go ahead and pull this over so we can see the full screen here. Alright, there we go. Alright, so I just reproduced the picture down here. And what we want is a car starting at the bottom of the hill down here. Alright, goes all the way up to the tunnel at a constant acceleration and constant acceleration, that's it. Okay? And at the time that the car starts going up the hill, the drone over here is also fired at this initial angle beta at a speed vm, okay, in this direction. Alright, and so as these two objects are traveling in whatever way they do, at the same time this car reaches this tunnel entrance, which is a height h above where it started, we want this drone to also hit the car and destroy it because it's full of terrorists or something like that. Okay? So, where do we start? It's the number one question. I had about 10% of you guys ask this question. Alright? So in general, do we have a sketch? The answer in this problem is yes. So for this problem it's taken care of. But in general, the first thing you want to do is draw the sketch with the objects involved and the relevant heights, the relevant distances, all drawn in there as well. Okay? Next thing is make a coordinate system, one which will make your calculations especially easy, right? So the more experience you get, the more likely you will be to choose a coordinate system that is convenient for your calculations. And that is why we recommend that you practice a lot of different problems, right, using different coordinate system choices before going into the exam. Alright? And in this problem, we have a coordinate system defined for us. So what are the things we're looking for in a coordinate system? A well-defined origin and a well-defined positive x direction and positive y direction. Looking back up at this picture, we have our origin defined here, right? And the positive y direction vertically up, and the positive x direction to the right. Perfect, okay? So we have both of those things taken care of. Good and good. First things that you want to do when you start a physics problem are these, okay? Without these, your position functions, x of t and y of t, will not make any sense whatsoever. And also the directions of your velocity and acceleration will be totally arbitrary without defining your positive x and y directions. Okay. So some more things to consider are how many objects are moving, and hopefully you address that before you make your sketch, okay? So if there are two objects moving, then we need two sets of position functions. In other words, two sets of x of t and y of t. Why is that? because the position of the car, which is going to start at the bottom here as a function of time, is going to take on its own set of x and y coordinates as it moves up this hill, independent of the x and y coordinates of the drone that is fired off to the right. Therefore, we need two sets of x and y coordinates for the two objects that are moving in this problem. Okay? And now to start the mathematics of the problem, we isolate each object, in this problem being the car and the drone, and we start with their accelerations and obtain their position functions through integration. Okay, so in the format of the test, the test questions will be formatted so we have a law and definition, application, and result. Under the law and definition section, we are going to put, well, given that we know the accelerations, which are given to us in the statement of the problem, make sure you reread it if you did not realize that, okay? We are then able to find the position function, x of t ultimately, by, well, this is half of the position function, by integrating the acceleration to get velocity, and then integrating that result to get x of t. The same story with y. We have acceleration in the y, we integrate to get velocity in the y, integrate that result to get y as a function of time. Okay, so now let's get down to the application section. So where do we start? Well, we start with one object being the car. So write car, underline it, right? And that's what we're starting with. And we want to start with the acceleration, all right? Because we are given the acceleration. And given the acceleration, actually, and the initial position and the initial velocity, we know everything about the motion of an object, okay? So it's a good idea, given the acceleration, to start with that. And before you go ahead and start doing the math, go ahead and just draw the acceleration vector. Why is it a vector? Because we are working in 2 dimensions. It's 2-dimensional motion, right? This car can not only move to the right, but it can also move up, all right? So this acceleration, which is, so the car is accelerating along the direction, along the incline of the ramp. So this acceleration is going to have a component in the x and y direction. So here's a picture of the acceleration vector with the given magnitude a1, all right, which is constant, and it's given that we're accelerating up the ramp, so at an angle theta. And from there, we can then draw a triangle, right, which will then give us the x and y components of acceleration. I just put absolute value signs around it because sometimes we have positive and negative components, and when we're dealing with a triangle, we always want to take the absolute value of those components so that we're only working with positive lengths, okay? Okay. In this case, though, we have acceleration pointing in the positive x and the positive y, so ax and ay will be positive. All right. So, we've drawn the vector, we then know the x component, so just start with one component, x, the x component, and find x as a function of time, all right? So ax is a1 cosine theta due to this triangle here, right? Cosine theta is equal to ax over a1, therefore ax is equal to a1 times the cosine of theta. Okay, so according to this formula up here, right, we ultimately want x of t, so we need v of t. To get v of t in the x direction, we integrate a in the x direction. So, integrating a1 cosine theta, which is just a constant, and you must realize this because theta is a constant, so the cosine of theta is a constant. a1's a constant, so the product of the two is just a constant, right? When we integrate a constant, we get the constant times t, a1 cosine theta t, plus an arbitrary constant c. Now, about 9 people are still very confused about how to deal with these arbitrary constants. So once and for all, let's put this to rest, and I will show you how to figure out what these arbitrary constants mean, okay? So let's just write c this time. For the next 4 times or whatever that we use arbitrary constants, we will go ahead and fill in their physical meaning. All right? Physical meaning. Okay, so what you do is you write the function vx of t with its arbitrary constant c. Okay, so that's just summarizing this result here. All right, and then the trick is to evaluate the function at the time 0. All right, Vx evaluated at the time 0 is equal to, all right, so plug in a 0 for t here. 0 for that t, and we get 0 plus c. All right, now just read this equation from right to left. C is equal to Vx at 0. What does that mean? That means that the arbitrary constant in this equation is equal to the x component of the velocity evaluated at time t equal to 0. Okay? That's exactly what it means. All right? So then you just rewrite the result with the arbitrary constant plugged in. All right? And how do we know it's v1 cosine theta? Well, what I recommend you doing here is when you run into the initial velocity, go ahead and draw the vector. So we have the positive x. Always draw your vector using a coordinate system that has been given to you. All right, and v1 is up the ramp, right? So it's at an angle theta, and it has a given magnitude of v1. All right. So the components of this initial velocity v1 in the direction of theta are given by just simple trigonometry, and they're going to be the initial x velocity and the initial y velocity. Okay, so the initial x velocity here is v1, the magnitude times the cosine of theta, right? And that's why we have this here instead of vx0, right? Because we specifically know that. And if we specifically know information, we need to plug it in, all right? If this were unknown, then we leave it as just vx at 0. But since it's known, we're plugging it in, all right? Now we integrate vx of t according to this formula. We want x of t, so we integrate vx of t. Let's proceed to do that. All right, so we integrate this first term. It's a constant times t, so we get 1/2 times the constant times t squared. All right, plus, I'm sorry, I skipped down a line. Okay, once again, we need to get position, the x coordinate of position as a function of time. So we integrate vx of t. So we get the constant a1 cosine theta times t squared divided by 2. So 1/2 in front. And let me get this play button out of the way. Not sure why it's here. Should go away soon. Okay. Maybe if I take this out of here. There we go. Alright. So the next term is v1 cosine theta, which is a constant. So the integration of that is a constant times t. So v1 cosine theta t plus the initial x coordinate of the car. That's our constant of integration. If you don't believe me, put a c there and then evaluate this function at 0, and you will see that this constant is equal to this function evaluated at time t equals 0. Okay? And how do we get the x coordinate of the car at time t equal to 0? We just look at our picture. And in our picture, we have the car starting at the origin, so its initial position in the x direction is at t equal to 0, is at x equal to 0. Sorry. Okay? Proceeding, we now need y as a function of time. So to get it, we start with the acceleration in the y direction. Right? Ax was a1 cosine theta, so ay is a1 sine theta. All right? Vy will be a1 sine theta t plus the initial vy by integration. So we're integrating this, right? And this is a constant of integration. And some people ask, okay, that doesn't look like a constant. Why are we calling that a constant of integration? It's vy with a parentheses and a 0. Usually a constant is just one letter, okay? Well, all right, that's understandable to be confused about that. Because this is a function, but evaluated at one time. And when you evaluate a whole function at just one point, you're going to get a constant, right? You evaluate y equals x at x equal to 1. You get 1. That's a constant, right? Okay, so this is, in fact, representing a constant, all right? And once again, all right, you should know where that arbitrary constant comes from by using the trick I described above. Okay, and the initial velocity's y component for the car is v1 sine theta. We then integrate Vy to get y of t. So we integrate a1 sine of t to get 1/2 a1 sine of theta t squared. And then we integrate v1 sine theta to get v1 sine theta t. And then plus the constant of integration, which is just the initial y position of the car. So I put a subscript c there to represent y position of the car, because we're also going to have a drone to deal with later. And once again, it's starting at the origin, so the y-coordinate is 0 at time t equal to 0. All right, now the drone. So if you reread the problem, you'll see it tells you that the drone has a component of an acceleration which moves to the left and one which moves up. All right. So remembering that acceleration is a vector, right? So it's just some vector in space. They go ahead and give us the components, nicely enough, to be negative c2t squared, and they give us the y component to be c1t upwards. All right, and that's going to be the acceleration of the drone as a function of time. All right, so the x component, we start with that, and using the same exact process as above, we integrate to get the position function. Okay, so go ahead and see if you can follow through this on your own. We integrated this to get this, where the constant of integration is the initial velocity's x component for the drone. And if we read the problem, we'll see, drawing the initial velocity vector here, that the initial velocity of the drone is up at an angle beta, right, with a magnitude Vm. Now, it's very important here that we notice when we draw this vector in the coordinate system, as we should properly do every time, it points in the second quadrant. And in the second quadrant, x values are negative, so the x components of these vectors are negative, and the y components are positive. So this velocity vector, which points in the second quadrant, should have a negative x component and a positive y component. All right? So this Vx evaluated at 0 is negative Vm cosine beta. Make sure you understand that. And for the x coordinate, we go ahead and integrate each term here, right? And we get this result plus the initial position of the drone. Well, what's the initial x coordinate of the drone? We go up to our picture. We go up to our x-axis. All right, here's the x-axis. We trace it until we find the drone. There's the drone. All right, the drone's up here at this x coordinate. And although I have not put it here, the problem has drawn for us that this distance is equal to d. Okay, so this x coordinate, right, should be d. Very good. All right, and while we're at it, let's get the initial y coordinate. Right. Well, we're also told that this distance here is s. Right. So the initial y coordinate of the drone, well, this is y equals 0 down here, and we have to go up to a height s. So the initial y coordinate of the drone is s. So let's just keep that in mind as we proceed. Okay. So we left off here. And this x coordinate, the initial x position of the drone is d, so we get this result for the x coordinate of the drone. For the y coordinate of the drone, we have to start with the acceleration in the y direction, integrate once. Our initial y velocity is Vm sine beta, and it's positive, right, as we described above. And the y coordinate of the drone is obtained by integrating each term here. And this constant of integration is going to be s. Make sure you understand that, right? If you've been following along so far, you'll understand why this is s. Okay. So part C of this problem is, what are the conditions for the mission to be successful? Okay? And if you go up to my clarification up here of the problem intends that in order for the mission to be successful, the drone must hit the car when the car reaches the tunnel. Okay? So we need to express those things mathematically. We don't want a written sentence here. We want math going on. Okay? So we have the coordinates x and y of the drone, right, and the car separately, all right? So what we need to happen is we need, well, at the time that the car reaches the tunnel, for its x-coordinate to be equal to the x-coordinate of the tunnel, and for the y-coordinate of the car to be equal to the tunnel, at that one specific time that it reaches the tunnel. And then at the same time, in order for the car to explode, after it's been hit by the drone, it has to, the position function of the drone in x and y have to be at that same exact place. So let's look at the picture, and this hopefully will clarify everything. My verbal explanation was not that great. So the car starts here down here at time t equal to 0. It will move up the ramp, okay? So it then goes up the ramp, and it reaches the tunnel at a time t equal to capital T. At the same time that the car reaches the tunnel, okay, the drone started at t equal to 0, all right, and it hits the car at the tunnel at t equal to capital T. So t equal to 0 here for the drone, and then it traveled over to the tunnel, and it should get there at the same exact time that the drone gets there. That the car gets there. Then the drone will hit the car, and there will be an explosion. The mission will be successful. So now let's express that in terms of mathematics. Let capital T, it's important that you write this sentence, let capital T be the time that the car reaches the tunnel. The x-coordinate of the car, so x sub c means the x-coordinate of the car, evaluated at that time t, capital T, must be equal to the x-coordinate of the tunnel here. Okay, so how do we get that? Well, we know that the tunnel has a height h, and the angle of the hill is theta, so using trigonometry, if we call the x-coordinate of the tunnel L, we have the tangent of theta is equal to h over L, so the x-coordinate of the tunnel should be h over tangent of theta. Okay? And in addition to the x-coordinate of the car being at this, the x-coordinate of the tunnel, it also must be at the y-coordinate of the tunnel, which is h, at the time it reaches the top, by definition, right? Okay, now at the same time, the x-coordinate of the drone must be equal to the x-coordinate of the car, right? Which is the x-coordinate of the tunnel. And the y-coordinate of the drone must be equal to the y-coordinate of the car, which is the y-coordinate of the tunnel. Therefore, we have the drone and the car meeting at the entrance of the tunnel at the same time, capital T. And these are the conditions which must be true for the mission to be successful. The next example is the vector quiz we did in class. Okay? So we were given, well, as a quiz, we were given a vector with magnitude A defined at the angle theta A from the positive x-axis, and the vector B defined from the angle theta B from the positive y-axis. Find the sum of the two vectors and call it vector C. Okay? So for the law of definition, we write the rules of vector addition, all right? And it's as simple as this. You have a vector, you want to break it into components, and when you have another vector, you can break it into components, all right? And if you want these two vectors to work with each other through addition, through vector multiplication, which we will learn about later, we want to then just work with the components of the vector, all right? So, if A, written in component form, is axi plus ayj, B, written in component form, is bxi plus byj, then the vector C is equal to ax plus bxi plus ay plus byj. If you're totally lost as to where any of this is coming from, you absolutely have to revisit the chapter on vectors before the exam. Otherwise, you will be in big trouble for this exam. Just a friendly warning, okay? Seriously, though, you really need to understand vectors to have a chance in this course. So please, please, please review vectors if you are having any trouble with this. Okay, so the application part of this problem, we have to then write ax and ay, the x and y components of the vector, all right? common mistakes. I'll put these in red. People write AX is equal to A cosine theta AI. This is not right because the component of a vector is not a vector. It's a scalar, okay? And scalars don't have direction. So when you write the component of a vector, you just write the value in no direction, all right? So there isn't one, right? If you look up here at how vector A is defined, it's AX times I hat plus AY times J hat, right? There is absolutely no direction involved. And just so I don't confuse you guys, because I know the notation in the book uses arrows, I'm going to go ahead and put arrows here, right? So the little hats sometimes are put on top to show that it's a unit vector. And I've gotten into the habit of putting these hats there, but the book's notation does not, so we will leave them off and just put arrows, okay? Okay, so for vector A, we have, if we look at the picture, it's just a nice right triangle we can make and split this into components, all right? So this component's AX, this is a right triangle, and AY, and this magnitude is A, right? So we can go ahead and write, using simple trigonometry, the components. Now, B, vector B is a little different, right? Because its angle is defined from the y-axis. And notice the vector B is in the second quadrant. In the second quadrant, vector's components are, well, for the x direction, the x component of a vector is negative, and the y component of the vector is positive. So this vector B should have a negative x component and a positive y component. So, using trigonometry here, you will see this is bx, or the absolute value, because we want to use lengths, and by, okay, no, not by there, but by, sorry, here, okay? So the absolute value of bx is going to be b sine theta, okay? So we have b sine theta b here, right? And we have a minus sign in front because it has a negative x component, as we've explained, all right? And so the y component is going to be b cosine b, all right, b cosine theta b, so make sure you check the work up above. So under the results section, we go ahead, use vector addition here. The sum of the x components gives us the sum, right? We can call the cx here altogether, ax plus bx, but it will give us the vector sum x component, and the sum of the y components gives us the vector sum y component. So we take ax plus bx, giving us this first x component times I, and then ay times plus by, right? And there we are. And let me go ahead and put arrows here again so that we're all familiar with the notation. All right? Okay. So one other thing is that the magnitude of A can be written like this, or just with the letter A. Both are okay. All right? And some other common mistakes, I'm trying to think of them. Oh, when you have a problem with two angles, make sure you don't just write theta. Write theta A or theta B, referring to the angle that's given, right? If it's called something else, you then just follow the label that they give you in the problem. For example, sometimes they use the Greek letter phi for an angle. All right? Okay. So that is it. And good luck on the exam next week, and study hard. Bye.